I will be talking about transactional tasks, which are a mechanism to introduce parallelism in software transactions. So in this paper, we studied two concurrency models, futures and software transactional memory. Firstly, futures are a concurrency mechanism which allow parallelism to be introduced in a program. And futures provide two constructs, fork and join. Fork takes an expression, it creates a new thread, and it starts evaluating the expression on that thread. And a fork returns a future. Join then takes this future, it waits until the thread has finished its execution, and then returns the result of that thread. And there you can see a classical Fibonacci function, and by simply wrapping the recursive calls in a fork, this function is executed in parallel. Secondly, transactions are a mechanism that allow a memory to be shared between threads. And software transactional memory provides four constructs. A ref creates a transactional variable with initial value v. Atomic encapsulates one or more expressions in a transaction. And then in that transaction, you can use dref and refset to read from and write to transactional variables. The syntax I use here is based on Clojure, but the semantics are similar both to Clojure and Haskell, as well as other STM systems. And here you can see a traditional example of an application that uses STM. It consists of two bank accounts, both of which are encapsulated in a transactional variable. And then two threads are created, each of which contain one transaction. The first transaction transfers 10 euros from the checking to the savings account, and the second transaction sums the balances of both accounts. And since transactions are serializable, that means that either this transaction is executed before this one or the other way around. But in both cases, this program will print you own 600 euros. So it is never possible for the second transaction to observe the state between these two statements. In this paper, we studied the combinations of futures and transactions. So if you try to create a future inside another future, this is nested task parallelism, which we saw in the first example. In case you try to create a transaction in a future, you get regular use of transactions, which we saw in the second example. If you create a transaction inside another transaction, this leads to nested transactions, and these are well studied in literature. However, if you try to create a future inside a transaction to introduce parallelism inside your transaction, this can lead to several problems, and this is what we studied in this paper. Throughout this presentation, I will be using the Labyrinth application as an example. And this application combines futures and transactions. This Labyrinth application consists of a grid of cells, and each of the cells is represented as a transactional variable. And the input to this program is a list of source and destination points. And the aim of the application is to connect each source point with its corresponding destination points using non-overlapping paths. So one of the use cases of this application is in chip design, where you want to connect transistors using electrical wires that cannot overlap. This program looks as follows. So for each of the points in the input, first we create a copy of the grid, and then we do an expansion from the source point to the destination point through this grid. And this expansion happens using a breadth-first search algorithm. So this algorithm will expand each point and write the costs to its neighbors. And this write happens using a ref set. So this continues until eventually the destination point is reached. And at that point, this trace back function will trace back a path from the destination back to the source. And then the add path function will write this path to the shared grid. Now, if we want to execute this application in parallel, we can simply create a new thread for each of the iterations of this for loop. And by wrapping this piece of code in a transaction, we ensure that this is safe. Because if two transactions would happen to find a path that overlaps, then a conflict will occur on the cell where they overlap, which means that one of both transactions will abort, roll back, and retry, and attempt to find another path that does not overlap. In this application, a transaction is created in future, and this works as expected. However, if you run this application, you will see that the speedup is very limited. So as the number of threads increases, you get a very modest speedup. And this happens because of two reasons. First of all, as the number of threads that execute in parallel increases, the chance of conflicts between these transactions increases. And secondly, this application contains very long transactions. The whole search process is encapsulated in the transaction. So that means that in case of a conflict, the transaction rolls back and it needs to re-execute the whole search process, which limits the speed up. So a way to solve this is to introduce parallelism inside the transaction, and that's what we do here. So in this code, we replace the sequential search algorithm with a standard parallel breadth first search algorithm. And this algorithm will expand each of the points in parallel. However, if you try to write this program, it does not work because because of several problems that occur when you try to create threads in a transaction. So first of all, if you try to write this program in Clojure, it does not work because threads created in a transaction do not have access to the transactional state of the encapsulating transaction. So in this code example, if you try to access a transactional variable inside a future that was created inside a transaction, this won't work because at that point you do not have access to the transactional state. If you try to solve this by wrapping this ref set in another transaction, this will create a separate transaction. However, this inner transaction is independent of the outer transaction. So that means that the inner transaction can succeed while the outer transaction fails. And this violates the serializability of the transactions. On the other hand, if you try to write this program in Haskell, it also won't work because Haskell forbids you from creating threads in a transaction. So if you try to call fork.io, which runs in the IO monad, in a transaction which runs in the STO monad, the type system prevents you from writing this program. So in effect, Haskell limits the amount of parallelism you can exploit. And to solve this, we created transactional tasks. So first of all, we want to allow parallelism in a transaction. So that means that we allow threads to be created in a transaction, and these we call transactional tasks. We want these tasks to be able to access the transactional variables. So that means that each of these tasks should adopt the context of the encapsulating transaction. Furthermore, we want, so to prevent race conditions, we want these tasks to be isolated. So that means that each task should work on its own conceptual copy of the data. And finally, we want to maintain the serializability of the transactions. So that means that all tasks that are created in a transaction should join before the transaction can commit, so that it can commit in a single step. And on the other hand, if a conflict occurs in one of the tasks of the transaction, then all of the tasks in that transaction should abort, so that the transaction as a whole can roll back and retry. So if we look at this in a bit more detail, so to realize this, each transactional task contains two data structures, a snapshot and a local store. The snapshot of a transactional task is a conceptual copy of the transactional state that existed when the task was created. In our actual implementation, we do not need to create copies. We can implement this more efficiently. But conceptually, this appears as a copy, so to the developer, it appears as if a copy is created. And secondly, each transactional task contains a local store, which stores the modifications that were made to the transactional variables in that task. So now, whenever a transaction is created, we create one root task, and the snapshot of this root task is a conceptual copy of the transactional state at that point. And the local store starts empty. Then later, when you write to transactional variables in this task, these are written to the local store of that transaction. Then, when a child task is forked in this transaction, we create a new transactional task. And the snapshot of this transactional task should be the state that existed at the point where it was forked. So the snapshot of this task is the snapshot of its parent modified with the local store of its parent, and you can see that here. And the local store of this child starts empty. Then in this child task, you can write to transactional variables, and these are stored in the local store of the child. And at the same time, you can write to variables in the parent task, and these are stored in the local store of the parent. So that means that both of these tasks can run in isolation. Then finally, when the child task is joined back into its parent, we need to merge the changes of the child back into the parent. So that means that we need to merge the local store of the child into the parent, and that's what we do here. So here, this 2 is copied into from the child back into the parent. However, if you try to copy this 2, we encounter a conflict because this transactional variable was also modified in the parent since the task was created. And to solve this, we allow the developer to define a conflict resolution function. So whenever a transactional variable is created, we allow the developer to specify a resolve function that should specify what happens when such a conflict occurs. And this resolve function takes 3 parameters. So as the first parameter, it receives the original value of the transactional variable. So in this example, that's null. And this can be found in the snapshot of the child. And a second and third parameter, it takes the values that exist in the parent and in the child at this point. So in the example, both these values are 2. And then this function should return the new value for the transactional variable, which could be the value of the child or the parent. Or in the case of in the example of the Labyrinth application, it could be the minimum because these numbers represent costs in a search algorithm. It could also be the sum or even an error. Transactional tasks have several useful properties. First of all, they make it possible to introduce parallelism inside the transaction. Secondly, they maintain the serializability of the transactions. So we require that all tasks created in a transaction, all changes of all tasks created in a transaction are joined into the root task before the transaction commits. So that means that the commit can happen in a single atomic step. Thirdly, tasks are coordinated. So either all changes of all tasks are committed in this single atomic step, or in case a conflict occurs in one of the tasks of a transaction, then all tasks in that transaction are aborted and the transaction as a whole can roll back and retry. And finally, we provide determinacy in the transaction on the condition that the conflict resolution functions are deterministic. And this means that since each task runs in isolation on its own separate copy of the data, the order in which the tasks are scheduled does not affect the end result of the transaction. So if you now go back to the Labyrinth example, now we can execute the code that I showed earlier. And so in this graph, the blue line represents the version with the sequential search algorithm, and the other lines show the versions with the parallel search algorithm. So in the line at the bottom, we use the parallel search algorithm, but inside each transaction, we only create one task. So the difference between the blue line and this line is the overhead of switching from the sequential to the parallel algorithm. And then the other lines show what happens when the amount of threads created inside each transaction is increased. And what we see is that on this particular hardware, a maximum is reached for the case in which 2 transactions run at the same time, and inside each transaction up to 8 threads are created. And this happens because at that point the chance of conflicts is minimal and the cost of a conflict is reduced. So since each transaction can execute faster, that means in case of a conflict it can also re-execute faster, and this makes conflicts cheaper. The Labyrinth application was one application of the STAMP benchmark suite, which is a benchmark suite of applications that use transactional memory. Another application in this benchmark suite is a base application. And this application spends around 93% of its execution time in a transaction. And if we look at the speedup of this application, we see that as the number of threads increases, the speedup levels off. And if we examine the code of this application, we see that in its main transaction, there is a for loop, but each of the iterations of this for loop is independent. So we can simply execute each of these iterations in parallel, and then we can exploit more fine-grained parallelism. So while in the original version, not enough work was available to keep all of the processors busy, in this new version with a more fine-grained parallelism, we can keep all of the processors busy, and this way we get a higher speedup. So based on these experiments, we can conclude that, first of all, for the Labyrinth application, that by parallelizing the search algorithm, we got fewer and cheaper conflicts, leading to a higher speedup. For the base application, we could introduce more fine-grained parallelism inside the transaction, allowing us to better exploit the processing power of our hardware, and again leading to a higher speedup. We also saw that this required only a low effort from the developer, certainly for the base application, where it sufficed to execute each iteration of the for loop in parallel. And since we reuse existing concepts, so the same features that existed outside transactions can now also be used inside transactions, this requires only a low mental effort from the developer. And based on these experiments, we conclude that transactional tasks are suitable for applications that contain long transactions and that spend a lot of their execution time in transactions. So transactional tasks have been implemented as a fork of Clojure, and this is available on GitHub and in the artifact that accompanies this paper. And in the artifact, you can also find the benchmarks that I showed. And I didn't really go into detail in this presentation on how we can implement this efficiently, so without making copies. But these details are in the paper. So to summarize, we saw that introducing parallelism in a transaction can be useful for programs that contain long transactions, but currently this is either not allowed or it breaks the serializability. And to solve this, we introduced transactional tasks, which are threads that can be created in a transaction, but with safe access to the transaction, to the encapsulating transaction. And these transactional tasks have several useful properties. They maintain the serializability of the transactions, they are coordinated, and they provide determinacy in the transaction. And based on experiments, we saw that there are several benefits to using transactions. First of all, they allow you to exploit more fine-grained parallelism, leading to a higher speedup. And they require only a low effort from the developer. This concludes my talk. If there are any questions.
Can I say something without asking a question?
Yeah, okay.
It's a great idea.
Okay, thank you.
Can you elaborate just briefly on how you do implement this efficiently, and how did it a significant departure from what Clojure already did, or
yeah,
or similar?
So I changed how. So normally, Clojure keeps track of all transactional variables that are modified in a transaction in a map, and in my implementation, this turns into a tree of maps. So whenever so if you are in a transactional task, you can first look up locally what the value is of the transactional variable you're accessing, and then you can go up a tree to go back into the into your parent task and so on to look up these values.
Hi, great talk, thank you. Do you know of any efforts to bring this to Haskell?
No.
No. Are you looking to?
I looked at Haskell, but it's much more complicated to implement it. Well, Clojure is based on, the SCM in Clojure is written in Java, so it's quite easy to extend it, while the SCM of Haskell is much more complicated.
That's all the questions.
Okay.